the webinar. So go ahead, Sam.
Okay, thank you, Susie. I'm hoping everybody can hear me since I'm on my speakerphone. And I also want to apologize for there was a lot of delays and problems to try to schedule this. One of the major issues is that for a lot of the experiments that we've been doing, we conduct the work in Japan, and it's difficult to sort of give these kind of webinars, for example, like 3 a.m. local time there. Even if I drink a lot of coffee, I'm not really interested in talking about this at 3 a.m. basically. So probably people could realize. And today I'm going to be talking about a lot of research we've been doing over the last several years, trying to simulate wind-driven firebrand showers, or I like to use the word attack, that occur in these kind of fires. So the presentation is organized as follows. Basically, I'm going to be giving an overview of the NIST Dragon technology. And I think in the past when I was invited, I know Steve Quarles gave a presentation from IBHS, and you've actually probably already seen, in their wind tunnel, they're basically using our Dragon technology. So if you're familiar with that facility, you're going to sort of see how the Dragon was basically started here at NIST. And I'm going to be talking about other experiments we've been doing to looking at firebrand generation from building components as well as structures, and talking about how we've been improving our Dragon technology, as well as a series of different workshops that we've been organizing. In fact, Chris Dykes joined one of these workshops last year that we had in Tokyo. So for this audience, I don't think I really have to talk about this that much. I mean, these are just some nice images of wildland-urban interface fires. There's a preference here on California. So there's obviously been a lot of fires in California and a plethora of images that are available. But what you're seeing in these images, basically, especially on the top, is which I like to refer to sort of firebrand storms. It depends. People like to use the terminology embers, or I think firebrands is a more scientific terminology. So generally, I've stuck with that. And what we're seeing is that these type of storms are responsible for a lot of ignitions of the structures in these fires. But unfortunately, it's one of the least researched things, as we're going to talk about. So if you actually look at a lot of post-fire investigation studies, here at NIST, my colleagues have been involved in that, and but many post-fire studies have also been done for many, many years in the literature. And if you go back and you look at this, both in the U.S. and also the work that's been done in Australia, they always seem to come up with one major finding, and that's that firebrands are responsible for a lot of the ignitions. So clearly, it's important to understand these firebrand processes if you want to understand ignition in these fires. And I just put a bunch of bullets here. This is not sort of my grandiose idea. I mean, these have been major recommendations from a variety of organizations. I'm probably sure most of you have read the Royal Commission report in Australia, and I'll be talking about some work we've been doing with Australia related to that. And the image I'm showing you here, I thought that was just particularly cool. This is an image that actually was taken from the International Space Station. It was just directly taken with one of the astronauts' cameras of the fires that occurred there in 2013. So that just shows you the scale of these events. And, I think everybody on the phone is aware of this, but I think it's pretty interesting just to see that the scale of these type of fires that occur, that you can basically just see this from an orbiting space station. One thing that's important, I guess, to realize is that, before I do any research, I always like to ask myself, who even cares about this? Having a PhD and doing lots of other kinds of research, I find myself in many presentations listening to people talk about things that I'm not really sure who even cares about that other than that presenter, to be honest with you. So in this case, there's obviously a lot of organizations that care about this. I've listed some of them. And obviously, if you live in the WUI, I mean, you obviously care if you're a homeowner. Right? I think that's a very important aspect of this. Obviously, if you're living in these areas, which are quite prevalent in the U.S., you would care whether anybody's doing any research or trying to improve the resistance of these communities to these kind of situations. So if you look at firebrands, you can imagine it in a very simple point of view, which is related to the generation, the transport, and the ignition. Unfortunately, if you look in the literature, almost everybody's been studying the transport for like a long time. And I mean, more than 40 years. And what it is that there's a whole bunch of models that people have developed, and they sort of incrementally change these models to look at the firebrand transport. But the problem is that nobody knows, for example, like what are the vulnerable points on the structures that the firebrands may potentially enter, or, for example, what I like to say, where the rubber meets the road is, where do the firebrands actually ignite things? I mean, and that hasn't been studied. And one of the main reasons is it's actually really difficult to try to replicate a firebrand attack. I mean, I showed you those images earlier, and you clearly need to sort of develop entirely new experimental methods to do this. So some of the goals of our research are, we'd like to develop the scientific basis for new building codes and standards, as well as scientific basis for retrofitting construction. And ultimately, the goal essentially is that, you know, you have to design these communities and structures to try to resist these type of ignitions in these particular fires. I mean, that's one very pragmatic approach to deal with this problem. There's many, many WUI communities in the country, and unless you basically somehow deforest the entire country, you're going to have WUI fires. And obviously, deforesting the country, I think, is not an idea that anybody would think is a good one. So how do we make these structures more resistant to firebrand ignitions? So I'm going to be talking about the development, which we call the NIST Dragon, and you're going to see why it's called that in a minute. And one problem that we've had is we're not able to get the movies to work from the webinar, so Susie is going to be showing this movie here. So whenever you're ready, Susie, you can show this. One of the first things we wanted to do, basically, was if we wanted to design an experimental facility to generate firebrands, we wanted to understand, well, what do firebrands even look like? And what the movie should show, assuming we can get it to play, is an image of a series of experiments we did at NIST to basically burn different types of vegetation and collect firebrands from it. And so now the movie should be coming. What I want you to get the impression from this is this isn't rocket science. It's basically trying to determine what type of firebrands are being produced under different moisture contents. And as I said, in the firebrand area, this research was basically never done before. I mean, people were busy trying to understand models, assuming firebrands are spheres or other kinds of interesting geometries, and then lofting them. But if you asked people what are firebrands, what is the distribution of firebrands from something that's burning in realistic fire situations, nobody could answer it since nobody did any experiments. So what you basically should gather from that is, you know, we're collecting this kind of information and trying to determine what type of firebrand sizes are being produced from different kinds of vegetation. So we could stop the movie now, Susie. And so with that information, once I get back to the screen, I guess I could advance it. But so we were able to collect firebrands from these type of burning vegetation. This is Douglas fir in this case. We've also studied some other conifers as well. And here's some data that you see, basically. These are some firebrands that are being produced. Mainly you get a lot of cylindrical geometries. And this is just showing you a different size conifer trees and the kind of firebrands that are being produced. And once again, just to repeat, I mean, this isn't rocket science, but it just, this kind of data basically didn't exist because nobody had conducted these kind of measurements. The other work we've done basically with CAL FIRE was CAL FIRE did an investigation post-fire study on the Angora fire that occurred in 2007. And as part of that investigation or study, basically a series of trampolines were found to be exposed to wind-driven firebrand showers, and as well as other kinds of furniture, for example, like couches, not couches, but basically like cushions that you have on outdoor furniture and these kind of things. And these were studied to basically try to determine if we can learn any information from the potential firebrand sizes that will be produced. There's an entire journal paper about this in the journal Fire Technology, so I could refer you to that if you're interested. But basically what you're seeing here in this image is the trampolines were collected, and basically we could do a digital analysis of the burn patterns that were produced. And what we found basically was that a large percentage of the firebrands that were creating these burn patterns, you know, are very small in size. For example, if you look at these projected areas versus the percentage, you see that the great majority of the holes that are produced are very, very small. And the Texas Forest Service actually used the same methodology in their fires that occurred in 2011, and also observed similar things. That there were like lots of small wind-driven firebrands that were being produced and causing these kind of burn patterns. And we also have the capability, I'll talk about later with our facility, is we actually took the same samples of the trampoline and exposed that to firebrands in our laboratory, and actually were able to reproduce or see similar type of burn patterns. So if you deposit a firebrand on these trampolines, you actually see a hole indicative of the firebrand that was deposited on that material, basically burning through to make that size. So this brought us to the idea of, can we develop an experimental apparatus which allows us to generate firebrand showers in a repeatable and safe fashion, of course. One thing you probably realize is if you've done any experimentation with fire, when you're trying to study this phenomena, you don't want to try to burn down your laboratories or other kinds of things like that. Obviously, that would be a problem. So we developed a generator, and the idea behind this is actually not complicated. I mean, when wood burns, its density decreases. And so what you do is you basically can load in different kinds of materials into this device. We've used a variety of materials. Here I'm showing a Norway spruce mulch that we've used. And basically, depending on how you filter these materials, you load it in, and then you ignite it. As you ignite it, you provide a very low flow of air. You can see this blower here. And since the wood density is decreasing due to the combustion process, the firebrands get generated and want to get lofted out of the device. And the idea is if you could then implement or couple this device to a full-scale wind tunnel, you could then create a firebrand shower that you would see in a realistic situation. So we've been doing these experiments in Japan. As I mentioned, IBHS had developed a wind tunnel very recently in the US, a very, very large-scale wind tunnel. But basically, the Japanese have had this wind tunnel for more than 10 years before that time. So we've been doing this research there since 2006 using this Dragon. And this wind tunnel is a very nice facility because it's very easy to do basically component testing of structures. It's a 4 meter by 5 meter cross-section with a 15 meter test section. So the size is basically ideal for this kind of research. And if you've been to Japan, it's about 40 minutes north of Tokyo. So I think several of the people on this webinar probably attended our conference last year and were basically there as well. So this is a picture of the Dragon, and then here's where we're going to show you the last movie. We're not going to try to show any other movies after this. We have a YouTube video about this, which probably some of you've seen. It has funny music, so if you're interested in that, it's interesting to listen to it on YouTube. But I'm just showing you this because when we tried to show the video, it ran into some issues. It was slow. But what you're going to see basically is the Dragon producing firebrands inside this large-scale wind tunnel in Japan. And I think it gives you some sense. If you look at that, you can then sort of put whatever you want downstream of that and expose that to different type of firebrand showers. And so once that movie is closed, I'll then advance to the next slide and talk more about what we've basically been doing with this technology. Okay, thank you, Susie. So if I could advance this, yeah. The first thing we wanted to do is start exposing different kinds of building components to wind-driven firebrand showers. One of the first things we wanted to do is that if you're familiar with roofs, there's a roof test standard that's been on the books for about 100 years. It's called ASTM E108 or UL790. And the images on the top, what you do basically is you build a 1.2 by 1.2 meter section of a roof, and you simulate firebrands by putting burning cribs. The biggest is a Class A crib, which is basically a foot by a foot, that one that you see on the top. And the idea is you try to measure the penetration through the roof. Now, if you can imagine, if you were to do those experiments with a ceramic roof, ceramic doesn't burn, so you wouldn't expect a lot of penetration. But what you see if you look at an actual ceramic roof in the field is there's all these gaps that occur at the edges. And so the current test method doesn't address those particular gaps. And there's been research to suggest, and also a lot of post-fire studies as well, that clearly firebrands might be capable of being blown underneath these gaps and potentially causing ignitions. So what we did basically is we used the Dragon to expose ceramic type of roofs. And I'm just showing you, there's a reference to the paper that we published on this. And everything that that I forgot to mention, everything I'm showing you today has already been published in different journals. So afterwards, if you're interested, I'll just let you know. I can send you the links. you can see these kind of phenomena. The firebrands will blow up under these tiles and cause ignitions. And so this clearly shows that there's limitations with the current testing methodologies for roofing, since they don't simulate this dynamic firebrand attack that you're seeing in real fires. So what we did is we did some recent work with, in collaboration with the Tile Roofing Institute in the US, in collaboration with the Australians, and this came related to the Royal Commission in Australia as well, is that, since all we've tested with those ceramic or so-called Spanish-style roofing, as you know, in California and other places, there's also a lot of concrete and terracotta tile roofing. So basically, you don't have the large gaps that you have in the Spanish style, but you have, a couple millimeter gaps between the tiles. And so the question is, do the firebrands still penetrate those gaps? And if they do, is it possible for them to cause any damage to the underlayment that you would have with the roof? So what we did in these experiments is we constructed the roofs based on the Australian constructing methodology. So what you have basically is a series of battens that you're seeing there. And what they're using is a fire-retarded underlayment. They call it sarking, so it's an interesting terminology. And so the idea behind this is that if you do these experiments, will the firebrands penetrate these tiles and cause any damage to the sarking? So these are the tiles. And what you can see basically in these images is that there are about like a 2 millimeter gaps that occur within the tiles. So you don't have the large gap spacing that you have in those Spanish-style tiles. But the question is, does it penetrate? And we did these experiments. There you see the dragon unleashing attack on one of these roof assemblies. And we have a report about this as well. And there's a lot of quantification in terms of what the fluxes of firebrands that are being sent to it and all this. And I'm not going to go into that detail. That's in the report if people are interested. What you would be interested to see is even under those gaps, the firebrands are still penetrating. What happens is they burn on the tiles, they don't quench, and then they go through those particular gaps, and then actually they cause this kind of a burn patterns on the sarking itself. So of the 4 different type of tiles that we tested, 3 of them resulted in this kind of penetration and basically melting of this sarking material. This is important also to realize is that in this version of the firebrand generator, this is a non-continuous version, so we only provide about a 4 to 5 minute attack of firebrands. And I'll talk about later, we've developed a newer version of this device that is continuous. So it lets us develop firebrands for a longer time. But even under such a short exposure, about 4 minutes, you're seeing this firebrands are penetrating the tiles and melting this material. When we tested the flat terracotta tile roofing assembly, we didn't observe any penetration. And one of the reasons is these particular tiles actually have an interlocking design. You can look at it in the report. But if you can imagine, there's an interlocking design with like a groove. So what happens is the firebrands get trapped within the grooves of those tiles and are unable to escape. So this is why in this particular case you don't see that. But in all the other cases you had a penetration of the tiles themselves. The other thing we wanted to look at was firebrand penetration through building vents. In California, in the previous building code, it recommended a 6 millimeter mesh behind a building vent. So when we inquired about why that 6 millimeter mesh, what was the basis for that, my understanding is it was designed to basically like mitigate rodent infestation into the vents. There was no testing to really figure out what firebrands would do under those cases. So what we did is we did a whole series of experiments where we basically exposed vents with different types of mesh behind it. So what you're looking at are 3 different meshes, 6 millimeter, 3 millimeter, and 1.5 millimeter. And in all cases, the firebrands basically obviously get through the vent because the vent spacings are very large, but they actually would burn on these mesh, these metal meshes, and then eventually penetrate and go through. And then beyond that mesh, we basically just put some samples of shredded paper to figure out whether it was possible to cause any ignitions. And in all cases, we basically observed ignitions. So these experiments showed that the 6 millimeter mesh wasn't really helpful in mitigating the firebrands to be infiltrating the structures. So we then did a whole new series of experiments. This was work we did in collaboration with Steve Quarles and ASTM, where right now in ASTM, they're trying to develop a test methodology for firebrand-resistant vents. And so we did a whole series of experiments with them to try to understand basically, in more detail what would happen. So we actually looked at a whole different types of ignitable materials behind the vents, and we looked at mesh sizes down to 1 millimeter to sort of see what's going on. Here is the schematic of the wind tunnel in Japan. So you're seeing that the Firebrand generator, or the Dragon, is located here. And we place the structure there about 7.5 meters away, and then basically you attack this structure with that vent. This is a typical experiment. So you're seeing the Dragon unleash these attacks. And basically what you see is that as you reduce the mesh size, so what I'm showing you here is mesh size is going down 5 millimeter down to 1 millimeter. What you see is that for paper, and then this is cotton, and then what we had behind it is a crevice. So basically what you can imagine is just a oriented strand board with a 2x4 crevice. And what you see is that Firebrands are penetrating even the 1 millimeter mesh. But in general, of course, as you decrease the mesh size, it shows that it's harder to get ignition under certain kinds of materials. But you're still getting penetration in other kinds of issues that are occurring due to that. These are just some images, what you're seeing. These are the cotton samples. So what the Firebrands would do basically is they would just burn holes directly through the cotton. And then this is the crevice. You're looking top down. So we did experiments where we filled the crevice with shredded paper. Shredded paper was just indicated like any kind of maybe like a fine fuel that somebody might store in an attic space. And what you see is that, you get these kind of ignitions from the Firebrands that are penetrating. And this is behind like a 2 millimeter mesh. So the Firebrands are just penetrating and going through and causing these kind of ignitions. This is helpful, I think, just to understand the dynamics of what's going on. You see the Firebrands arrive on the mesh, and then they burn down and they pass through the mesh. And then basically these Firebrands then land into those ignitable materials. So the experiments basically showed that if you only use mesh, it's not effective. I mean, the Firebrands are still going through, but as I mentioned, as you reduce the mesh size, it becomes more difficult to actually ignite materials because, as you can imagine, the Firebrands that are penetrating are basically smaller. So back several years ago, we worked with CAL FIRE as part of the Building Standards Commission in Australia, where basically the mesh size was reduced from 6 millimeter down to 1.6 millimeter to 3.2 millimeter. Clearly, Firebrands were still penetrating under smaller mesh sizes, but also at that time, there was no standardized testing methodology for Firebrand-resistant vents. So this was a good practical solution to try to improve the situation. But right now, ASTM is still working very actively on developing this Firebrand test standard. And it's obviously the ASTM process is an open process. Anybody could vote who's a voting member. So it's not clear when the standard will pass, but it's something that's actively being worked on and trying to come up with that type of methodology. The other thing we wanted to look at basically was related to eaves. Many people believe that the eaves themselves are a place where Firebrands would accumulate under the eaves and cause ignition. If you're familiar with eaves construction, you have basically open eaves as well as boxed-in eaves. And I'll show you a picture, but in an open eave, you have the roof rafter tails are basically exposed, and they extend beyond the exterior wall. And then if it's boxed in, obviously, you probably can understand boxed in meaning it's closed. So the question is, do the Firebrands accumulate in these eaves? Anybody that's an architect will appreciate this drawing. This basically shows you a typical rafter tail to an exterior wall. This is typical construction that would be used in California. And it's just showing you how the construction works. If you're an architect and you could read that, you'll appreciate it. Probably if you're not an architect, maybe it's not helpful, so I'm going to show you a picture in a minute. This is what it looks like in terms of the construction. So what you're looking at here is normally in a house you would actually have siding applied here. But what you're basically seeing here is these are the exposed roof rafter tails. This is the open eave. And also in many areas they actually vent this. So what you're seeing is these are 50 millimeter, they call it blocking, but vents. And then behind this vent we also placed mesh to see, do the Firebrands accumulate here and do they actually get to the mesh and pass through it? Here's a typical experiment. So, we didn't bother to put any siding on the wall because the idea here is really trying to understand what's happening in the vents and the eaves. So that's why you're just seeing regular oriented strand board there. What we actually saw is that when you have vents, the number of Firebrands that actually arrive at the vents was actually very, very small, basically. Under different wind speeds, these are 7 and 9 meter per second. So 9 meter per second, to give you some idea, it's almost 20 miles an hour. And what you're seeing basically is we didn't see any accumulation within those open eaves. And when you had the vents, like, even though we're like basically directing many, many firebrands at these structures, we only measured very few that actually could even get to the vent location and eventually like go through. And the thing that's probably interesting for people to realize is that during these experiments, the base of the wall itself actually ignited. So what you're seeing there is the wall itself is actually ignited due to the accumulation of the firebrands. So even though the firebrands could get to the vents, it didn't seem like the vents located under the eaves were really a major issue for firebrand penetration based on these experiments. The other thing we basically were doing was related to firebrand accumulation. A lot of our research has shown that it's actually the accumulation of many of these small firebrands that cause ignition. This isn't just a picture I've taken with a long exposure with my camera. So what you can actually see is the firebrands under long time exposure. And what we've done here is put different obstacles in the flow to simulate different types of conditions. And you can see that the firebrands will accumulate in front of these obstacles and result in interesting kind of phenomena. This is also just an experiment showing if you have a fine fuel located in front of a structure. Here what you have is the dimensions on this are basically an 8-foot by 8-foot wall with mulch located in front and a window. And what you're seeing is that the mulch is ignited and you get smolder ignition and then transition to flaming ignition. And as you can see, the vinyl siding and the wall, they don't seem to enjoy that burning mulch, as you can see the situation there. So this experiment was basically stopped since we want to look at the vulnerability, but since I have to clean all this up after every experiment, I really didn't want to have this huge mess of melted vinyl in the wind tunnel. So after we got this ignition, we basically stopped this experiment. The other thing now we're looking at is also related to firebrand production from building components and structures. Clearly, firebrands are produced when vegetation burns, but for example, once the fire gets into the community, the structures themselves are fuel. And this is something that I don't know a lot of people realize. So the question is, are firebrands from structures, are they significant? Are they similar to vegetation? I think my colleague Ruddy Mell might be on the line, but Ruddy's doing a lot of work related to simulation of these kind of fires using WFDS. And the question is, well, you need to understand firebrand production from burning structures when you do these kind of models because it's very helpful as source terms. And finally, we'd like to be able to look at using the Dragon to simulate a whole range of different firebrand shower conditions. So what we've done basically is embark on a whole series of experiments trying to collect firebrand generation data from actual structures. So one of the first things we've done is we worked with, in California, we worked in Dixon, California. Those of you who have been there, it's a small town outside of San Francisco. And they did a whole series of experiments where they were doing firefighter training. And they invited us and allowed us to instrument some of the experiments. And so after they finished the firefighter training, they did a burn down of the structure, and then we collected the firebrands from this. Then what we did is we went back to the laboratory and did experiments of components, specifically of walls, and tried to understand, do they provide any insights? Because, for example, as interesting as it is to burn down structures, as you can imagine, it's very expensive, it's very time-consuming. So you want to try to see what kind of insight you can get from laboratory type of conditions. And so I'm going to talk about how this relates to that. And the idea is to try to develop a database of these firebrand generation from these kind of materials. So we did this experiment in partnership with the Northern California Fire Prevention Officers. What was interesting is when they did the experiment, that's the actual house they burned. They were responsible, two different fire departments in California, the Vacaville Fire Department and the Dixon Fire Department. The wind speed that day was about 6 meters per second, which is very windy. So I didn't think they would end up doing the experiment, but we ended up doing it. And as you can see later, a lot of firebrands were generated. We placed a series of water pans at different locations around the structure. And the reason we use water is that you want to quench the combustion, because when the firebrands are generated, if you just let them land on something, they'll basically be burned away. So you want to be able to sort of freeze that process and see what kind of firebrands are generated. And this shows you where we collected this. Here's some images of the house. So it took about 2 hours for it to basically burn down. Here you're seeing it's early on, about 30 minutes after ignition. Here you see it's basically completely burned down. We were here in the background with our instrumentation, and the entire city of Dixon came out to watch this fire, so they were very interested in us too, since they thought our instrumentation was something from, I don't know, Mars or something. So a lot of the children found that experiment very, very interesting to sort of watch what we were doing. And the fire service was great and very helpful for this, and we really appreciate all the help that they gave us to do this work. So now I'm going to shift the focus. I'll show you the data later, but to talk about basically what's going on with building components. So what we did then is we said, well, what happens to firebrands that are produced? What if you just burn individual walls, and if you burn individual corners? Architects like to use the terminology reentrant corner. What it means is it's an inside corner in your house. And so the idea was, what if we burn these walls and see what kind of firebrands that are produced? And also, does it give us sizes indicative of what you might see from a realistic house? Once again, we did these experiments in the full-scale wind tunnel in Japan. Here's a layout, and we had a whole array of water pans here. And these are the kind of images you generate. So what we did is we developed an ignition methodology using a burner, and we ignited these walls, and under the wind, basically, we collected the firebrands. And you can see very interesting pictures that are developed and the actual detailed generation process of the firebrands from walls. So what I want everybody to take away from this is it's obviously not easy to do any kind of experiment, but doing an experiment of walls is obviously far easier than trying to look at an entire house, basically. And here's some data. I apologize, it's a busy graph, but what you're looking at basically is the area of the firebrands that are generated versus the mass. And what we're showing here is this is a whole series of vegetation firebrands that we've measured, as well as a whole series of structures. And what you can see is that you want to look for some similarities and differences in the data. A majority of the firebrands we collect are basically smaller than 1 gram. Here's 1 gram, so you're seeing a lot or less than 1 gram, and smaller than an area of about 10 centimeters squared. Then the other thing we wanted to do basically is, can we use like sort of a structure itself and burn it down in a wind environment and see what kind of firebrands might be generated from that. So what you're looking at here is another experiment we did where this is a structure, and basically what you're seeing is a series of pans that were generated here. And here are the images that are produced. So what we did is in this structure we have a sofa, and we ignite the sofa, and the sofa produces intense fire which results in flashover of the compartment itself. And basically then we burn down this entire structure, and then we collect the firebrands that are being produced. Once again, to us this experiment isn't it's nothing groundbreaking. I mean, it's how can you do an experiment to sort of look at an actual structure burning under well-controlled wind conditions and see what kind of firebrands are being produced? But very few type of experiments have really ever been done. I mean, there's only one other experiment we know of, and that was done by the Japanese for Japanese-related construction. So this is the only experiment that we know of that's been done for this. And what you can see is you can compare all this data. So you can try to understand, for example, how do these firebrands compare to the real house burn that was done? You know, if you're not an experimentalist, you would still appreciate that burning a real house is very complicated. There's a lot of things that are difficult to control. So you want to see what kind of information you can learn from that. So we have all this data plotted here. And once again, these are the comparisons in the individual building components. So what you're seeing is that the simple experiments from the components give you some insight in terms of the firebrand generation that you're producing from these other kinds of far more complicated situations. And then finally we wanted to compare, the only data we know of in the literature was a work that was supported related to nuclear winter applications back in the 70s. And the idea behind those experiments was if there was a nuclear disaster, how, you know, when the fires that are produced from that, how would firebrands be produced and these kind of information. So you can find these reports, they're published. One is by Vavarka. And what he found is that he burned a whole series of different buildings and actually also found some similar results. That basically, like, very small firebrands dominated the distribution of what was being produced. For example, of the firebrands that he collected in this experiment, you can see that, like, these are the areas. I mean, there's a huge number in the very small areas. So a lot of small firebrands that are being produced from the combustion and burning of structures, similar to what we're showing with our experiments earlier. Here's a detailed comparison. Once again, a lot of data, but there's publications of all of this, so you're more than welcome to send it to anybody that's interested so you can read it. What you're looking at here is comparison of those individual building components, which are very simple, to the real-scale structure we burned in Dixon, California, as well as Vavarka's study. So you can see that there's some similarities and differences in terms of these results. One thing that's interesting is Vavarka found a very large number of small firebrands here. And one thing that's not clear is, of course, in his experiments, he used plastic sheets. What he did is the firebrands that landed on the plastic sheets basically burned through and made these holes, and then he measured the holes. In our case, we're using water, so actually we're collecting the firebrands themselves, quenching it from the combustion, and then we extract it from the water and then measure the sizes. So it's not clear whether the differences are due to those different measurement techniques, but in any event, you still see there's similarities in the different size classes that are being produced. And then this is an experiment compared to Yoshioka. Yoshioka is the only other data we know where they've done an experiment under wind in Japan, and it shows that they're using Japanese construction materials, so it's difficult to say how applicable it is to California or U.S. WUI problem, but it's still useful to compare to see what kind of size classes of firebrands that are basically being produced from this. And now what we've been working on is obviously going to siding. So we've been looking at cedar siding, for example. I know in California, you guys like a lot of cedar siding. That's a very common application. So what we've done is actually burn walls of cedar siding themselves under different wind velocities. And what you can actually see is when you burn cedar siding, you actually get a lot of very, very light but very large firebrands that are generated. So when you do these experiments, for example, you can see these giant burning cedar firebrands actually blowing out of the wind tunnel itself. So this is a very interesting result, I think, as well, and shows that you also have to look at the effect of the siding on other kinds of things in terms of the firebrand generation process itself. So in the remaining minutes, I want to go over we have an improved Dragon. The original Dragon I mentioned was a batch device, so we were limited to how much we could load and the firebrands would be generated. But what we've done is we've redesigned it and made it to be continuous. And also we've created a facility which we call the Dragon's Lair, which is a bench scale apparatus that lets us look at, for example, specific materials to firebrand showers on a bench scale. So here's the bench scale. We call it the continuous feed baby dragon. We like to come up with a lot of funny names. But basically, it's smaller than the regular Dragon, and this is something that actually we have at NIST. And we feed it with wood pieces continuously, and then it generates firebrand showers. And we have a small-scale wind tunnel at NIST. Obviously, this is nowhere as big as the BRI wind tunnel. It's about 50 centimeter by 50 centimeter cross-section by 2 meters. So much smaller than the 4 meter by 5 meter facility. In BRI, obviously, you can walk around in it. We can't walk around inside this. But this lets you evaluate different kinds of materials to firebrand showers to sort of see what they do. So here's some images of we just put in cedar crevices in the device, and then you're exposing it to continuous firebrand showers. So what I'm showing you here is that this is the feed rate of wood that we feed into the Dragon, and this is the time to smoldering ignition. So what you can see is as you feed in more firebrands, and also we've determined, and you can see in the paper, that this feed rate will correspond to a certain generation rate of firebrands. You get ignition much more quicker depending on how much firebrands are basically being generated. So it's a very useful, I think, device to look at. Obviously, you can't look at systems with this. You can only look at individual components of materials. But it's helpful to give you some idea, for example, of what materials might be more resistant to ignition from firebrands as compared to others. And then we've actually built the new full-scale continuous Dragon. There it is sitting in Japan. And this lets us feed in wood pieces and then generate continuous showers for however long you want it to do. So one of the things we've done, there's been a lot of studies, but we've done decking work. We've actually looked at wood decks. And from post-fire studies that have been done here by my colleagues at NIST, as well as talking to the fire service, decks are believed to be a problem in these WUI fires. For example, the wood decks catch fire and actually ignite the structure itself. So we did a whole series of experiments looking at how wood decks ignite under continuous firebrand showers, and this is the kind of data you see. The firebrands accumulate on the deck surface, they cause ignition, and what's particularly interesting, of course, is that after the deck itself is ignited, this image on the bottom is actually taken, so the wind tunnel's already been turned off a long time ago, and you can see that it's still smoldering within the members, the support members of the deck. So this just shows you the kind of issues or difficulties you have in these kind of fires that you can easily get these kind of ignitions from firebrands, and you have this kind of smoldering ignition behavior that's occurring. And there's reports and publications about this as well if you're interested. And we also had a workshop in California before doing these experiments to get input from decking experts on terms and what type of deck assemblies we should actually test. One thing I'll mention as well here is that we installed it in a corner, but we put non-combustible board. This is gypsum board because this first series of experiments wanted to look at only the ignition of the deck. The next series of experiments are looking at once the deck's ignited, what happens to the wall? Is it easy to cause ignition to the wall itself, basically? So the idea is how the fire is spread from the deck to the wall. The NIST Dragon technology has been like cloned all over the place. I mean, I just want to mention this. So if you were participating in the IBHS webinar, you saw our original Dragon. There it is. They actually built, I think, 9 or 12 of these. It's a whole bunch because their wind tunnel's huge. Portuguese, they have the biggest WUI research center in Portugal. They built what they call the Portuguese Dragon, so it's our Dragon, but here you see it. And Japan has also built the Dragon's lair as well at the National Research Institute of Fire and Disaster. So it's being used by a lot of different people to shed light on this particular problem. I guess if you're interested, this is Dragon in Japanese, so in case you're curious. So we also have a special issue coming out in fire technology. One problem with the WUI fire issue is that it really hasn't received a lot of attention in the fire safety science community. And I think that's unfortunate since it's a really important problem. So we actually have a special issue coming out. It's already online, but it's actually going to be in print officially in January. So if you want to go to those papers, you can read it. And there's a whole series of papers discussing how we could, the idea is looking at improved building codes and standards for this kind of situation. Also, ASTM, we're having a symposium. It's already fixed for June 18, 2015. And as far as I know, it's the first ever WUI ASTM symposium. It's called Structure, Ignition, and WUI Fires. And we're going to be looking at papers. Obviously, anybody could submit a paper. It'll be reviewed, and it'll be, if it's up to muster, it'll be published in ASTM's journal. And the idea is we're interested in looking at studies and research that it could help improve building codes and standards for these kind of fires. And I'll close this presentation with the work we've been doing to try to bring different research communities together. Anybody that's familiar with Japan, they have tons of earthquakes and actually have a lot of problems with firebrands in particular. This is the Kobe earthquake. I believe the Kobe earthquake, it killed several thousand people in 1995. Here's a picture from this. Most recently, you're probably familiar, they had the giant earthquake, and everybody's familiar with the nuclear-related issues. But what a lot of people don't realize is that after those earthquakes, there were a lot of fires that occurred. And we have a paper talking about that as well as part of the workshop. But basically, obviously in Japan, there's no WUI fire problem. It's an urban fire problem because it's very densely built areas. But what's important to understand is the spread mechanism is the same. I mean, once the fires start, when it spreads within a community, it's related to the firebrand issue. So, for example, as the firebrands are blown by the wind, they land on structures and cause ignition. So there's a lot of benefit for both countries to try to work together to try to understand these kind of problems. So we have a special issue in Fire Safety Journal talking about these kind of interesting results, as well as if you're interested in learning more about the sort of post-earthquake fire spread in this particular thing as well. And we just had the workshop continued. We had one last year in Tokyo, 2012, and like I said, I think some of the people on the line were participated or were invited. And basically, there people actually got to see the wind tunnel we've been using and also get a better understanding of the situation. And this workshop is coming back to NIST in 2015, in March. So the first announcement has actually gone out, and we're now finalizing. The dates have been finalized, which I'll be sending out soon, basically. But the idea is to try to bring together the different fire science community into this problem and get more research and understanding of sort of what's going on. So in summary, I think I've presented a lot of information. What I want you to get away from this is that NIST has developed this Dragon, and it's a useful tool to basically try to understand what's happening in these fires. Before we had this Dragon, the truth is everyone was just guessing what the firebrands were doing. I mean, there was no way to really test any of these things. So now we can evaluate these type of things. Obviously, there's a lot more work that needs to be done. I mean, I think this is really just scratching the surface, to be honest with you. I know now, from my communications with Steve Quarles and IBHS, they're now running another series of experiments in IBHS But basically, as far as I know, I mean, other than the work that's being done in IVHS and the work that NIST is doing, I mean, there's no other experimental work looking at this important problem. I mean, and I think that's unfortunate since, you know, every day you see, every year, especially in the news, you see these fires, especially this past fire season, it's been a huge issue. Lots of structures that are lost, California, Texas, California. So the WUI fire problem is getting worse and worse and worse, and there's just not a lot of research, frankly, that's going on into this particular problem. And we've improved the Firebrand generator, so now it's fully continuous. What I didn't talk about, but we finished, is we've done a whole series of experiments looking at how mulch ignites under continuous Firebrand showers, as well as fences. We looked at actually wood fences also. So wood fences are an issue in terms of the Firebrand attacks as well. So we're going to be publishing that study soon. And some future work, I don't have time to go into a lot of detail, but we'd like to basically also start looking at different kinds of technologies. You know, there's a lot of technologies that claim that they could reduce ignition in WUI fires, but as far as we know, a lot of these technologies have never really been exposed or tested to any Firebrand showers. In addition, we're now actually building a new Firebrand generator, which we actually we're coupling to radiant panels to study the effect of combined radiation and Firebrand influence. So as you can imagine, when structures and vegetation burn in WUI fires, you have the radiation that's generated from these burning structures in addition to the Firebrands. So we want to understand how important are these coupled effects on these type of phenomena. And with that, I think I know we're supposed to keep it to an hour, so I know we've got only 5 minutes left. I apologize, but I'll try to take any questions that everybody has. Thank you.
Thank you, Sam. That was great. Very comprehensive, and I learned a lot. And I'm sure folks on the phone have some questions as well. I mean, folks on the webinar. Please go ahead and type your questions in the chat box in the lower left-hand corner, and we will work on those. I'm going to go ahead and bring up our conclusion screen and identify the questions. The first one for you, Sam, is from Bob Kowalski. He wants to know if there's a general distance from the fire line where structures are most threatened from the accumulation of firebrands.
I can't give you a general distance. I mean, I can refer you to our paper. What we've done is using the computer code that we have at NIST, we've actually done a series of like just numerical simulations where you can sort of use it to predict areas of stagnation. So for example, at different distances from structures, you get stagnation zones where you get the accumulation of the firebrands. And I can refer you to the paper. But depending on the kind of obstruction you have in the flow, you get these stagnation zones occurring at different distances from structures. And that's where these firebrands were observed to basically accumulate. So I could refer you to that paper. But right now, obviously, there's no general answer I could really give to that.
Okay, good. We had another question from Ruddy Mel. He said, were you able to weigh the structure burned in the BRI facility?
Yes, we did. One thing that we did is that paper, Ruddy, is actually now, it's coming out in Fire Safety Journal. We actually designed a load cell system that we protected from the thermal insult. And we actually weighed the entire structure and actually measured the temporal variation of mass loss. So we actually have that data. I could send it to you.
Great. So Chris Chambers wants to know, how would an older structure compare to the experimental structure components in terms of the fuel moisture of the wood? He assumes that older homes are drier and more flammable under typical WUI fire temperatures and humidity than perhaps your experimental temperatures and humidity.
That's a good question. One thing that we've actually done is, I didn't talk about it here, but it's in some of other publications. We've actually done some experiments where we actually varied the moisture content of the building materials. So what we did basically is when we did the walls themselves, we designed them in a modular fashion where we actually dried the oriented strand board sections in an oven and then basically put the wall back together. So we've actually done some variation of the moisture in these kind of effects. I haven't personally done a building survey itself to see how that influences it, but we've also looked at it in different ways with respect to, like, when I talked about the roofs, my colleague here at NIST, Alex Marangidis, has done a lot of the post-fire work. You know, when roofs age, for example, in realistic situations, the tar paper, for example, in his observations degrades and those kind of things. So we've also experimentally simulated these kind of effects. Also in tiles, you could actually have debris that accumulates under the tiles, as you can imagine. So we've simulated those effects as well. So clearly that's an important question, and we've actually looked at some of those issues. So I can point you to some of the papers that we've published on that.
Um, Great. So as far as that goes, are you thinking that you will follow up individually with emails, or you could actually, if you wanted to, send
People, I mean, I guess what
me
it
the
is
link
if the
and
people could just
we can
basically
send it out?
send me email. I mean, I know Ruddy very well, so I'm just going to send Ruddy the paper.
Okay.
But the other, I don't have the email from Bob, and I don't have Chris's email. So if they could basically just send me an email, I could just send that information to them.
Okay. Or Bob or Chris, you could put your email address in the chat box, and then we can make sure it happens as well. Go ahead and ask any other questions in the chat box in the middle column there. While waiting to see if there's any more questions, I'll just draw your attention to the box below the chat box, which is the web links box. It has live links. What you do to get to those links is you have to click on and highlight the link and then click the Browse To button. We have the Fire Science Consortium email list sign up. We have a webinar registration page where you could register for the 2 upcoming webinars I described earlier, and also an evaluation form to help give feedback about the webinar today and future topics that you're looking for. So please do go to those spots for us and give us feedback so we can continue to meet your needs. Are there any other questions? I see you're getting the emails there to
Yeah,
keep
I'm
track
actually
of.
got it. I mean, well, I guess I would like to ask Chris something related to his question, I guess. I mean, has he actually done any survey of the actual construction itself for the moisture?
Right, so Chris, if you have an answer, go ahead and type it in the chat box. We'll just wait a minute for those to come up. In the meantime, I'll just remind you what webinars we have coming up. We have one on December 10th with fire ecologists from the Central Sierra region of the U.S. Forest Service. They're going to be presenting on the rim fire and how vegetation looks post-fire on the Stanislaus National Forest. And on January 16th at 11, we have Molly Mowry, president of Wildfire Planning International, talking about creating fire-adapted communities. So if you go to the webinar registration page on the link there, you can find it. I'm not seeing additional questions. I do see, regards from Chris Dicus. And Chris Chambers did not really answer your question about having done anything in particular. Oh, there we go. He says, I have not, but he does fuels monitoring for prescribed burns and always thought homes would change in fuel moisture, something like the 1,000-hour or 10,000-hour fuels.
Yeah, I mean, one thing that I just wanted everybody to be aware of is, I mean, I did present a very broad overview of a lot of things and a lot of topics. So on one hand, I'm afraid I might have overwhelmed everybody, but at the same time, I think it's important. I wanted everybody to get a sense we've done a lot of work. And so, everything that I've talked about, there's actually a paper or a report. So if you're interested, I mean, I'm more than happy to send those links related to that. I mean, because I decided today, we have a lot of sort of fresh off the material that we've just come up with, but basically I didn't want to talk about that because I decided it's better to present everything that's actually already been published. That way, if there's questions, people could just directly refer to those publications.
Okay, I think that would be great. We actually send out a post-webinar email to tell people where the recording can be found. So if you want to send me some links, I can include that in the post-webinar email.
Yeah, one nice thing about NIST is I think like probably 90% of the papers we have it on the web that are fully like downloadable. So you don't have to even pay to get these journal papers. I mean, NIST has it online.
That's great, and that's unusual. So thank you. So with that, I think we'll draw the webinar to a close and thank everyone for attending. Let you know that the webinar was recorded, and you'll be getting an email that gives you the recording link if you want to pass that on to others who would be interested in this topic. And just thank you very much for attending, and thank you, Sam, for an excellent presentation.
And thanks again for being patient for me. Thanks, Chris, as well, because as you know, I think we tried to schedule this millions of times, and so we'll have to see. One thing that's interesting, I guess I'm looking at the thing, somebody named Guest said thank you, but I'm not sure who it is, so I guess we could figure out who that person is.
Well, thanks. It was obviously worth the wait.
Okay.
And stay on the line. I'm going to stop the meeting